Hello, I am Caio Santos, Research Associate at Fraunhofer HHI in Berlin. I will be discussing our work, Automated Dataset Generation for QoT Estimation in Coherent Optical Communication Systems. This talk is part of the demo that will be shown live at ECOC 2020 in Basel on the 20th of September. Before we begin, I would like to thank my colleagues, Behnam Shariati, Robert Emmerich, Carsten Smith-Longhorst, Kolja Schubert, and Johannes Fischer for their superb contributions to this work. Initially, we would like to briefly enlighten our listeners concerning the topic. Thus, we will be introducing the concepts of data sharing and its importance in the context of our work. Then, we bring a series of applications for usage with large amounts of data that are being discussed. We present the concept of reference dataset generation and our part in this field. Lastly, we present the concepts of our laboratory automation for experimental dataset generation before diving into the demo itself. Autonomous networking is one of the key enablers for digital transformation and moving towards low-margin operation regimen of telecom ecosystems. Thus, network data sharing or data sharing in general becomes fundamental in order for researchers to move towards better solutions within this scope. Many groups have generated in-house simulation data for their works, while experimental and field-collected data remain scarce in the public domain. This in parts due to the difficulty of generation of such data and or the unwillingness to share confidential aspects of the network of the provider. In this context, experimental data generated in telecommunication laboratories could work as a compromise between simulation and field-collected data. For this, extensive laboratory automation enables large measurement campaigns while minimizing human intervention. Before generating or acquiring high amounts of data, it is necessary to establish possible applications for such tasks. Here, we list some of the state-of-the-art applications for data-aided techniques that require high-quality datasets, such as machine learning-based QoT estimation, end-to-end learning for WDM systems, nonlinearity compensation based on neural networks, data-aided DSP-based monitoring, anomaly or fault detection, optical spectrum monitoring, or physical layer design. As can be seen, there is a demand for data in the telecommunication domain, and we wish to contribute to that cause. As mentioned before, the success of such techniques rely on the availability of large amounts of high-quality data. Starting with simulation datasets, Fraunhofer HHI has already made public its first portions of data to empower research in the telecommunications field. The image and link on the left represent our page for network data sharing, where all our datasets will be available. For now, only simulation datasets are present, but the work you're about to see within the demo demonstrates our next target for the development of large, diverse, and well-documented experimental datasets for the optical networking community. Since this is no easy job, we rely on laboratory automation to assist us with this task. This demonstration showcases a fully automated laboratory setup facilitating large-scale dataset generation. For this, first, 4 racks were prepared at Fraunhofer HHI's laboratory in Berlin in order to serve as our data collection platform. These racks contain a full WDM coherent system composed of transmitter, optical line system, receiver, and monitoring or measuring equipments. Having the system in place, automation scripts interact with one another to create a self-reconfigurable system capable of executing multiple experiments with minimal human intervention. Fail-safes and error management scripts help the system recover in cases of measurement or equipment failure. Only on the most severe cases a user has to intervene. With the automation and error protection in place, measurements are taken at each new configuration and saved for post-processing into large-scale, high-quality datasets. With the foundation of our work built, we can now dive into the demo and actually see the system in action. As mentioned before, this demo will be realized live at ECOC 2020 in Basel. A shorter version will also be made in the sequence of this video in order to enlighten the community regarding this work. Before beginning the demo, I would like to thank you for your attention and invite you to reach out to me with any questions or concerns regarding this topic. Thank you very much. So here we have a live stream of the lab where you can see the 4 racks that were discussed before: the transmitter, the receiver, the optical line system, and the measuring and monitoring sector. During ECOC, we will have 2 screens, so these will be shown simultaneously. You will have a live video of the lab and the dashboard being presented also, these together. since here for the presentation, it is better that I show one and then the other. So this is the dashboard that is shown in unison with the lab streaming. It is important to notice here, the first thing is the dashboard. This dashboard sets the pace of the automation of the whole system. So by following this dashboard, we can actually understand what the automation code is doing to the equipments and to the measurement campaign. As I execute the code, you will see that this fluxogram will be updated, letting us know what is happening within the code. So if we go back, we can execute the code. So an initialization of the system begins. Various instruments are being initialized in sequence. So we create a TCP IP or serial or whatever type of communication is needed with each of these equipments. And then we start an automation procedure after they have been initialized. As you can see, in the fluxogram already started updating. It passed through the instrument initialization, went to loaded the configuration table, and now we're setting the instruments for the first iteration of measurement. It will then measure the OSNR, acquire the waveform, and execute a DSP and save all the data. Since the configuration table is the very beginning of this step, we would like to start here. The configuration table actually shows to us what is being measured at each iteration. As soon as the first iteration is done, we will get to see all the values being updated within this dashboard. And then we will actually be able to see values from the configuration table, values from the telemetry from the systems, values from the DSP, and everything. This takes a while in the beginning, since the system has to set the instruments, has to set the configuration table, everything. After that, each update of the dashboard takes around 1 minute, which is the time for a measurement to be realized. So since the fluxogram says that it's preparing the data, the dashboard will be updated very soon. Now we get all the data from the first measurement and iteration. It then goes into the next steps. So back to the configuration table, we have now the configurations that are set for this dataset collection. So here we don't have many variations, because since this is a limited demo, we have a short time, we only put a couple of iterations. So the system will run the different modulation orders in 32 QAM and 16 QAM. This is actually programmed in the dock and configured in the DSP. We have a symbol rate of 32 gigabaud. We configured a distance of 0 or back-to-back and 340 kilometers, although we can also be measuring at 80 kilometers and 160. But for this example, we have 0 and 240. So we have 21 channels, but we will be measuring only channel number 11, which is the very middle. We could measure any of them, but for this demonstration, only channel 11. And launch power at each span, we will be measuring all of them at -1 dBm per channel. Channel allocation shows how many channels are dropped or how many channels are actually active within our WDM spectra. And so we have two different configurations, one where 5 channels are dropped and one where 10 channels are dropped. So when we see the full racks that were shown before, these racks are actually combined into a WDM coherent system. And this system is actually showcased in the setup above, where we can see values updating in near real time or after each iteration. So here we have the terminal transmitter with the signal generator dock, OMFT, the tunable laser, wave shaper to generate our dummy channels and to combine with our actual modulated channel. We have the optical line system where we have our EDFAs, our attenuators, and our fibers. Our terminal receiver where we have filter to filter out our channel, and the hybrid and the RTO to obtain our waveforms and thus perform DSP offline. and our measuring sequence, which is basically a switch that moves around according to what needs to be measured. So we're measuring spectrum to calculate OSNR, or to calculate channel power, and multiple other things like tilt, etc. And we actually have the receiver. So these points actually show where the switch is actually connecting. So the pink one, you can see that it's connecting to the switch and going to the receiver, whereas the red one goes to the OSA, and the blue one goes to the wave analyzer, which is also a spectrum analyzer, but of a different type than the OSA on the first one. So these points actually show where everything is connected. Each one of these values are updated from the equipment at every iteration, so you can see what's going on. So you can see the state of your VOAs. You can see the attenuation, the actual output power of your amplifiers, or the wavelength, etc. So these things are pulled directly from the equipment. On the right side, we see the actual spectra being measured. Since we have OSAs measuring before and after the filter, we can see the actual spectra that's before the filter, or the actual spectra that is being transmitted, but here it's actually being received. But of course, they're similar, just the impairments from the channel and the equipment, but in general, they have the same overall shape. And after a filtering, we have the filter channel here in orange. So you can see what is arriving and what is being filtered. As I mentioned, we're only analyzing the middle channel right now, but this could have been any of the other channels during a long measurement campaign. Below this is the OSNR measurement, where we actually obtain the OSNR. This is measured before the filter, so we can actually obtain the power of the channel and the noise level, as after the filter we would actually be losing part of the noise, and not losing the noise, but losing the side noise, and it wouldn't represent the true OSNR measurement. After that, we have this telemetry screen. This shows in a written sense everything that is in black and a bit more. So you get data directly from the terminal receiver, data from the optical line system, and this is all in a table and very summarized. We do not save just what is being shown here. Of course, we obtain a lot more information from the equipment. Not all of them are extremely relevant, but we save them nonetheless. Here, we're only showing the main ones. So, for example, what's the ETFA powers, what's the frequency of the channel, or what's the signal power and attenuation, for example, and the attenuators, and these sorts of things. Above the configuration table, we have system parameters, where it actually shows what system you're analyzing. So PDM QAM, we're now seeing a modulation order of 16 QAM, whereas before we were seeing 32 QAM. Symbol rate of 32, 240 kilometers at this iteration, and the configurations of the WTM grid. We also have a few QoT parameters such as BER, EVM, Q factor, OSNR, and SNR. After that, we have the constellation after the DSP. Both of these constellations, the top and the bottom, are the same. The difference here is that the top one only shows the color grade, and below it we have the EVM per polarization, so the EVM in X and the EVM in Y, whereas the bottom one shows a similar constellation, or the exact same constellation, but highlighted in red are the errors. So when you have a very noisy channel, or you have a very noisy transmission, you actually see lots of these red dots appearing. And when you don't have it, like here, which is actually a back-to-back measurement, for example, you barely see any errors. But this bottom constellation is very nice to see when you have very, very noisy channels, for example. And the last panel shows DSP parameters. So what's actually, once the waveform is acquired, DSP is run, and we have some DSP parameters so that the user can see what's being calculated and what's being compensated, or what parameters are being used in the DSP. So we have the front-end correction, for example, the CD compensation, which shows the estimated accumulated chromatic dispersion, the data-aided equalizer, which is run, the carrier phase recovery parameters, a DSQ DDLMS 4x4 equalizer, and the error counting system, which actually shows you the BR per polarization, how many errors in each polarization, and how many evaluated bits in each polarization are actually done. So as you can see, the fluxogram showed that this particular dataset generation has finished. So while I was talking and explaining, multiple different configurations were run. So we started out at 32 QoM, and then we moved to 16 QoM. We made many measurements at back-to-back and 240 kilometers, for example, and 2 different channel allocations. So each of these iterations was saved at the end of the cycle of the iteration, and then at the very end of all iterations, this is compact and saved in one single spot. All iteration data is saved in one single spot, and it shows finalized system, which is the system is over. Now, this next step is getting all this data, post-processing it, and actually generating the data set. Of course, this is only a demonstration, so this is a very basic configuration table. However, since no human intervention is required, you only monitor this and you only execute the code, you can put a very large configuration table and let this run for days or even weeks with minimal human intervention. And you can have a very rich data set with actual data measured from the lab. Again, the lab is always streamed live during the ECOC demo presentation, and we will be seeing this screen with the lab. It does not change much since you don't actually see many of these things changing. We have the log that will be running, and in the end, what we will be mostly looking at is the dashboard like we analyzed. So this is everything we have to show. Thank you very much for listening to our presentation. Again, my name is Caio Santos, and if you have any questions or inquiries, feel free to contact me. Feel free to reach out to us. Thank you very much.